Now there are certain factors that you need to keep in mind while using GPIOs that we will now get into, and these are things that as a user or a developer of systems that are going to use GPIOs you need to be aware of. First and foremost is voltage levels, right? Now every CPU or MCU has some kind of supply voltage that is provided to it. Common supply voltages would be 1.8 volts, they could be 3.3 volts. Depending on newer and especially low power microcontrollers, you might find that they go down below 1.8 volts. You could have 1.2 volts, and in certain cases, like for example the processors used in phones, they may even drop a little bit below 1 volt. The point is, that's the supply voltage that is given for the entire operation of the CPU. Now I could potentially have a sensor on the other hand that is running off another higher voltage, let us say 5 volts. Now the question is, the circuitry in here works with 1.8 volts, this one is providing 5 volts, and what that means is that when, let us say this is providing a digital high, this wire over here is going to get pulled up all the way to 5 volts. The question is that a problem? And the answer is, well, it depends as usual of course, but very likely yes, because what is happening is I have a CPU that is running only with 1.8 volts, I am trying to connect 5 volts to it. In order to really understand what is going on, you would need to know how this input buffer is built. At the end of the day, it is going to be made of some kinds of transistors and various circuitry of that sort. It might have some protection circuitry, it might not, right. The bottom line is, without knowing exactly how this is built and whether it is capable of tolerating a high voltage out here, you should be very careful of connecting something like this. Now of course there is an implicit assumption that the ground over here is the same, which is why I am only referring to the supply voltages in both of these cases. In reality, if you find that the grounds are different, you could end up with even bigger problems, right, because then there is something which you think is 5 volts is actually ending up showing up over here as a considerably higher potential difference with respect to this ground, right. Remember that ground is not something universal, it is a reference potential that is used for each circuit that you build, and unless you have some way of guaranteeing that both the circuits have the same reference potential, you could end up with something which looks like 5 volts to you over here, but looks like maybe 25 volts to this with respect to its ground. So that is something that you need to be careful about. Even if you have the same ground reference, connecting a 5 volt sensor directly to a 1.8 volt port could potentially damage the port. Similarly, you could end up with the opposite as well. You might end up with a CPU that is running on a 3.3 volt supply and a low voltage peripheral of some kind that only assumes that it has a 1 volt supply. At that point, if I take this and pull it up all the way to 3.3 volts, there is the potential that I am going to cause damage to this instead. Either way, unless you know exactly which way or rather how your circuits have been built, there is potential for damage, and that is the important takeaway over here. There is a similar aspect that comes in terms of current capacity, right. The previous one was with regard to voltage levels, but the same thing holds with regard to current capacity as well. An example of this is, we already saw the programming example of taking a CPU and making it drive an LED, making it blink. Now the point is, an LED actually requires a certain amount of current for it to glow, right. There is, and we will look briefly at how LEDs function, but I am not going to get into the details of the cut-in voltages and bias currents and so on. The important part is, for an LED to actually glow, some amount of current has to flow through it, which means that that current in turn is coming from the supply voltage which is going through the CPU or the microcontroller unit, right. And it is quite possible that this buffer that has been built over here is not capable of delivering as much current as the LED actually needs. Now if that is all there is to it, most likely what you will find is that, okay, the LED does not glow, right, you expect it to glow but it does not, right, which is okay, it is not damage as such, it is clearly wrong functionality. it is also the source of endless bugs and makes life very difficult to debug in hardware, right? Especially when you find that something which was working with a particular LED suddenly stops when you connect it to something else, because let's say this required maybe 12 milliamps whereas this was only capable of giving 10, right? So things like that can happen. What is worse is if you have the opposite. Let's say there is a sensor or some other kind of circuit out here that is somehow trying to make this voltage high and as a result actually drive in a current in this direction, right? And it's capable, let's say that for whatever reason the current that's coming in over here is 40 milliamps, right? Now there's a limit to how much current the CPU can take in and send to ground, because after all it has to still pass through the circuits present inside this microcontroller and then go to the ground potential. So there is a limit to what it can sink, the current that it can sink. In the previous case it was the current that it can source, over here it's the current that it can sink. If I try pushing in too much current over here, that will also damage the port and potentially the entire microcontroller. Now LEDs in particular, right, there are some interesting things that you need to keep in mind when you are actually building circuits with them. It turns out that an LED, it's a diode, right, and I can't get into the details of how diodes work over here. I'm going to assume that you are at least roughly familiar with the basics of what a diode is. The only thing that you really need to know at this point is this kind of curve is what's called the voltage characteristic of the diode, right. What it says is as the forward voltage across the diode increases, the current initially is very low, but then after a certain point it just starts taking off and then grows exponentially, right. And some particular voltage out there is usually taken as what's called the cut-in voltage or the forward voltage of the diode. Now as you can see, it's not like a abrupt on then off kind of behavior. So we usually take some reference point and say, okay, this is the forward voltage. But what these curves are showing is the different colored LEDs actually have different forward voltages. So for example, red LEDs typically have somewhere around 2 volts, green would be maybe around 2.5, blue would be closer to 3, white would be 3.5 or so on and so on, right. What that in turn means is that the actual voltage drop across the LED by itself when it is on is going to be around 2 or 2.5 or 3 volts, right. So if I have a 5 volt supply, there is some voltage drop happening across this and then going to ground. But now look at what's happening out there, right. We basically have the way the diode works is, let's say at 2 volts the current through it is around 10 milliamps. At 2.5 maybe it might have gone up dramatically, maybe 50 milliamps. And if I try raising this voltage all the way to 5 volts, I can't just extrapolate this line. What's going to happen is that the LED will probably just burn or blow up, right. And usually what happens is something called breakdown, which basically means that it literally the internal structure of the diode has broken down and it cannot be used again after that. So what do we do, right? We can't just leave it like this, because if I take a 5 volt processor, take its output, connect it over here, what's going to happen is this voltage will get driven to 5 volts. But this can only take about 2, at most 2.5 volts before it goes about to break down. And I don't have any other material over here that is going to absorb that remaining 2.5 to 3 volts of voltage drop, right. So that's probably going to end up causing damage to my circuit over here. It's as though you have taken 2 supplies of different, or taken a 5 volt supply and directly tried connecting it to something which is only 2.5 volt, which can take only 2.5 volts, right. Where does the remaining 2.5 volts go? If it doesn't have any place to sort of drop, then the whole thing is likely going to blow up. So instead what we do is we put a resistor in series, right, and this is called a current limiting resistor. And what we are doing is, okay, I have a 5 volt supply, I know that when my LED is on, the forward voltage across it for a good amount of current, let's say 20 milliamps, which will make it glow nicely and nice and bright at the same time without sort of damaging it, I say that maybe the forward voltage for that is 2 volts. This is just an example. It may not be 2 volts, but you can figure that out from the data sheet. What happens to the remaining 3 volts? It drops across this resistor, right? So now this actually gives me sufficient information to calculate the value of this resistor. How do I know that? Because I know that the current that I expect to be flowing through here is 20 milliamps, and I know that the voltage drop over here is going to be 3 volts. So if there is a 3 volt drop across a resistor and the current through it is going to be 20 milliamps, that basically tells me that the corresponding resistance is 150 ohms. Okay. So what do I need to do? I need to connect my LED and I need to connect a 150 ohm resistor in series with it before going to ground, and by doing that I can basically make sure that the current through this is going to be limited to at most 20 milliamps. The flip side of this is, of course, if I want the LED to glow very brightly and I want it to maybe have like 50 milliamps of current flowing through it, this resistor won't allow that. But usually that's good news, right? I don't want too much current to flow through it because it damages the LED after a point. I pick the current from the data sheet that is supposed to be the active, valid current for this particular LED. I check how much is the forward voltage drop it's going to have. I check my current and my existing voltage supply, and whatever remaining voltage is there, right, this 5 minus the forward voltage needs to get dissipated across this resistance. I choose a suitable value for that. This kind of current limiting is important. It's not just for LEDs, for pretty much any kind of circuit that is being driven from a port of a microcontroller. You need to check how much is the current draw that is going to be there and make sure that you are not trying to draw too much current out of this, and in short that you are not creating a short circuit. Now another variant of this is the current drive capability, right? In the previous case what we had was that if we were not careful about how we would connect things up, the LED might end up drawing too much current and therefore damage things. Now instead, if I am trying to, let's say, drive a motor, right, I might have a scenario where my microcontroller is only capable of delivering 5 milliamps of current, right, but the motor actually requires a lot more, let's say 100 milliamps of current in order to actually turn at the speed that you need. Now if you directly connect this up, it's possible that it works without damaging either the microcontroller or the motor, right, but the problem that's going to happen is the motor is just not going to turn. It may not turn at all, or it may turn at a very slow speed, much lower than what you expect. So what do you do, right? You need to be able to somehow pump 100 milliamps of current into this, but you can't get that out of your microcontroller. Could you use multiple different ports and sort of connect all of them up together like this? Bad idea, because almost certainly you're going to end up creating some kind of a short circuit over there, right? And anyway, what would happen is that whole 100 milliamps of current would then need to flow through the microcontroller and somehow come out over here, and that's not good for the microcontroller either. So what's the alternative? We break the circuit and add a transistor, right? Again, transistors, the way that I am looking at it is that it's a switch. You don't need to know too much about how transistors work, although it's good to sort of learn a little bit about the details of how transistors actually work in practice. For now, all that you need to know is they have these 3 functional terminals. One of them, right, is called, in the case of a bipolar junction transistor, is called the collector. In the case of a MOSFET, it's called the drain, right? That's connected to the supply voltage. There is another terminal which is either the emitter in the case of the BJT or the source in the case of a MOSFET, which can actually deliver a large amount of current. Basically the current would then come from the source through the transistor and out through this terminal. The critical third terminal over here, which is either the gate in the case of the BJT or the gate in the case of the MOSFET or the base in the case of the BJT, right, is just basically acting as a switch, or rather a switch control. What it says is, as long as I make this voltage high and deliver a small amount of current in here if necessary, right, it will turn the switch on and allow a large amount of current to flow here, okay, which means that by basically absorbing something possibly even less than 5 milliamps over here, it may be capable of delivering 100 milliamps on this side, right. Now transistors are commonly used for this, especially in things like motor drivers. You will come across specific motor drive circuits whose only purpose is to make sure that they can deliver a large amount of current for this purpose. There are also other circuits called relays that have a very similar kind of behavior. Once again over there you can activate the relay through a signal at this point and it will be able to deliver a large amount of current or voltage on the other side over here. So the important point is there is a very low control current but a high drive capability. It is able to deliver much more current onto the other side. Now once again from a functional point of view, when you are using certain things like push buttons, right, what you need to be aware of is that a push button is actually a mechanical switch, right. It actually physically is constructed of certain metal strips which when you press them down makes a contact and then the contact breaks again temporarily. Why does that happen? Because of bouncing. Literally the metal pieces sort of make contact, they then bounce off very minutely but enough to break the contact a large number of times. Usually what happens in practice is when you press a button, this kind of bouncing probably happens over a period of a few milliseconds, right, maybe around 10 milliseconds or so. It is too small to be felt by the human being, but as far as the circuit is concerned, 10 milliseconds is a lifetime, right. When you are running at let us say even 1 megahertz, right, 10 milliseconds is like hundreds or thousands of clock cycles, right. So even 100 clock cycles, right, would basically correspond to something which basically says, you know, by then you could have executed many instructions. You might have responded thinking that the signal has gone high, only to find that by the time you look at it the next time it's looking like it's low and then a little later it's again looking high. So what do? You need to debounce, you need to wait until the bounce period is over. There are a couple of ways of solving this. One of them is purely using hardware circuitry itself, right. Typical circuits include latches and custom debouncing circuits themselves. But in a lot of cases you can also get away by just solving the problem in software. Whenever you see a change in a signal, you register that change but then you wait for a few milliseconds, maybe around 10 milliseconds or some debounce time that you know based on your mechanical system, and look at the value again, and only if it has sort of remained at the same value for a certain amount of time you say, okay, now I need to respond to this, right. So the debouncing is sort of taken care of just through software. It adds extra logic but on the other hand is very easy to implement as well. There is another aspect of this which is not to do with how you implement the circuitry as such, but it's something called electrostatic discharge, right. And this happens because there is a buildup of static electric charge on surfaces which includes the human body, right, and includes your fingertips for example. This happens even more in dry climates than in humid or sort of rainy kind of weather. What happens in those cases is that some amount of electric charge has built up. Some of you may even have experienced this where maybe you wear shoes, you walk on a carpet, you go touch the handle of a door and there is a small spark, a metal spark that basically jumps between your hand and the door. That is actually electrostatic charge, right, which is causing a spark to happen. Now imagine the same spark happening into an electronic circuit, a microcontroller let us say. It would be a very tiny spark, it would be more than enough to completely fry your circuit and leave you with nothing else that works, right. And which is why generally we say that you should never directly touch the pins that are present on a circuit. You should make sure that your body has been discharged first before you handle any electronic equipment. And in fact the safe practice is that you should work at a ESD protected desk which has a strap which allows you to ground your body potential, prevent the buildup of such charge and reduce the chance of such kind of problems happening. Many microcontrollers and systems have some kind of circuit level protection for this, but it's definitely not foolproof, and in general you should always exercise caution when working with these things. This is all the more true of the GPIO pins that are present over there because they are meant for IO, they are commonly used for interfacing and so on, but they can run into problems if you are not careful with how you use them. So finally, a little bit about the examples where GPIOs can be used, right? We have already seen LEDs as sort of the most simplest form of doing something with a microcontroller. But apart from just sort of blinking and showing some signs of life, they are very important in sort of indicating the status of a system, and therefore you find that LEDs are very common in some kind of light, and LEDs in particular are low powered systems, so they do not really consume a lot of current. At the same time, they allow you to easily indicate the status of a particular kind of functionality, right. GPIOs are also commonly used to interface with button inputs. They can be used for driving relays or transistors to turn on or off other kinds of systems. And they can also be used for sensor interfacing, right. These could be of multiple types, either the analog sensors, as we will look at later, or sometimes even digital sensors, which are very similar to sort of push buttons, right, because they are all that they are showing is either a 0 or a 1 kind of state, but they can be used. And finally, GPIOs can also be used for certain kinds of communication, where you actually use them in order to communicate with a separate outside chip, right. Now, in a lot of cases, communication protocols are handled by custom circuitry, right, or custom modules present in your system that just take care of the communication alone. But if you do not have a particular kind of communication protocol, you can also emulate it, right, in software by using what is called bit banging. You are directly sort of putting out the protocol by means of modifying the levels of the different bits at a given GPIO port. This is uncommon but can be used, especially in scenarios where you don't have a particular protocol, but you are still trying to communicate with a device that only speaks that particular protocol. So these are different examples of where GPIOs can be used. As I said, these are the most versatile form of connection that is present in microcontrollers, but there are others and we will be looking into those in more detail later.